Welcome everyone. Let me present my screen. We will wait for a few minutes so that others could join. Then we'll start our session. Most of the lectures have been covered. So today's session and the next few sessions we are going to actually solve many problems. And so these two sessions I will highly recommend the students must join so that their problem solving skills will can be improved, and they can actually uh, get to know many other problems so that in the exam they can easily solve those things. Okay, let me just wait for 1 more minute and we'll start. Okay, then let's start. Okay, so welcome everyone. Welcome to the problem solving session of this course, Basic Thermodynamics, Classical and Statistical Approaches. The instructor of this NPTEL course is Professor Arnab Mukherjee of IIT Pune. This is the assignment solving session of week 10, And as you all know probably now, that I am Dibyendu. I am a Prime Minister Research Fellow uh, at IIT Kanpur. I am working in the Department of Physics, and this is my website link. You can check me there. There are contacts. You can contact me, and you can check the research activities that I carry out and the current research topics that I am interested in. And this is the YouTube channel, and where I post all these problem solving session, and there is a dedicated playlist which is in the same name of this NPTEL course, and I upload all the problem solving session by week wise, and you can check those content there. And if you haven't seen till now the previous contents or previous weeks assignment sessions, you can check them, and that will help you to prepare for exam. And if you like the sessions, please leave a like, please comment on those things, and I will be highly grateful. And please subscribe. Okay, so the first problem is quite easy. It says that at a local restaurant, 20% customer order takeout. Okay, so 20% of the customer uh, takes out the order. If 70% of the entire customer order take out and choose a hamburger, determine the probability that a customer who orders takeout will order a hamburger. So please pause if you are solving it offline. So please stop the video, and or please I will wait for a few minutes, and you can solve it. So I'll give one hint that you can probably guess that this problem is a conditional probability problem. So we have to find the probability of ordering a hamburger, given that the orders that people give, they take out. Okay, so I will give one hint. So this probability that a customer who orders takeout will order. So this and this problem boils down to find the probability of ordering a hamburger with a condition that this is a takeout. Okay, so try to solve it. So in the meantime, I can give you one hint that let's two event. First event, B is is B is the event of ordering a hamburger sorry hamburger, and event A is takeout order, and we need to find. So this is called conditional probability. Conditional probability. So you have to find that. Okay, I will give one more hint. This is the formula is P of B intersection A divided by P of A. Means that ordering that conditional probability of the probability of event B with the condition that A happens is probability of happening B and A simultaneously divided by probability of happening A. Okay, so please try to solve it. So it is pretty simple, right? So we know other probabilities because that probability of happening ordering burger and also ordering takeouts is this, because 7% of the entire order takeout and choose a hamburger. So if that happens, so first choose this, first determine this, what is the probability of takeout orders. So P of A is equal to probability of takeout orders is 20%, means 20 divided by 100 is equal to 1 by 5. Now probability of B intersection A, which is probability of ordering hamburger and ordering takeout is equal to 7%, means 7 by 100. And if you put those things here, 7 by 100 by 1 by 5, then you get 35 by 100 is equal to 0.35. So this is the answer. So the right answer is this. Okay. So in this kind of problems, the first important thing is to find which probability is being asked to find. So here the statement that the probability that a customer who orders takeout will order a hamburger means what is the probability of ordering hamburger given that that order is takeout. That is P, that is the same thing. That is the same thing. Probability of ordering hamburger given that the order is takeout. That is actually probability of ordering hamburger and that is also takeout. Means ordering hamburger and takeout. That is equal to probability, that is equal to 7% that is given, divided by probability of the condition upon which the whole premise is set, that is probability of A. So that is we have found out 7 by 100 divided by 1 by 5, that is 35 by 100, that is 0.35. Okay. It is something like that, out of total takeout orders, what is the probability that that takeout order will be hamburger. Okay, it is like that. That's why this kind of sample space, that is total, when we find the classical probability, we will write like this, the probability of happening this and probability of happening total. So here the total probability is somehow mapped to the probability of this event. So some kind of, in this sample space, how many times B happens. Okay. So should I proceed to the next problem? Okay. So the next problem says, determine the probability that the card drawn from a well-shuffled deck of 52 cards is a diamond, spade or club. So total concepts is here is the probability. So when there will be either or, I will give you one hint. When there will be either or, so there will be always summation. So that will be P, probability P of A union B union C, where A, B, C are the events of probability of finding diamond, spade and club respectively. Okay, so I will give one hint and then you will try. Okay, so always in this kind of probability thing, always try to focus on the language. So here the language is probability that the card drawn, that is this, is a diamond, spade or club. So if you draw a Venn diagram, okay, so this is a total thing. Now this is not a correct depiction because here this, there is no intersection between diamond, spade and club. So this will be then this, this is A, B, C. Here is also A, B, C. So the actual formula is, so we want to, so let's write that A event of getting a diamond. B is event of getting a spade. C is for club. Okay. Now since either or, since it is being asked that we have to find the probability of getting diamond or spade or club, then P union B union C, which is P of A plus P of B plus P of C minus P intersection B minus P intersection C minus P B intersection C plus P A intersection B intersection C. So it is like the area of this total. So if we like get area like this, A of A, then B, then C, then we have, and then we subtract this and this, then we actually subtract these ones, but this actually we have subtracted how many times? Three times. So 3 times we have included it. So when we are taking P of A, P of B, P of C, so in this middle region we have included 3 times. When we are neglecting A union A intersection B, B intersection A intersection C and B intersection C, we have removed this portion 3 times. So but we have to include this thing again, that's why this plus. Now for our problem this is very easy, but I wanted to convey the total message. So for our problem then, probability of A means getting a diamond is 13 by 52, which is 1 by 4. Same for will be diamond, sorry, spade, same will be for this thing. And there will be no thing of getting diamond and spade, because there is no intersection between these two, right? So there will be 0, because there is no card which has diamond and spade both. So B, this is called mutually independent. In C, P, A, intersection C, also like this also A. So the total probability then boils down to, sorry, P of A union B union C, it becomes P of A plus P of P plus P of C, which is 1 by 4, 1 by 4 plus 1 by 4, that is 3 by 4, I'll do 0.75. So this is the general scenario, and this is the our given problem. Okay, so I have solved it considering all the general considerations, so that this can be, so that you can solve any problem using this formula or using this concept, because there can be sometimes there can be intersection, and those events not mutually exclusive. Here A and B are mutually exclusive or independent. Okay, so that's the thing. Quite easy. Should I proceed to the next? Okay, so this is also a quite simple problem. Problem says a system of n non-interacting and distinguishable particles of spin 1 is in thermal equilibrium. The entropy of the system is, so we have to actually calculate total microstates, and if we calculate the microstates correctly, then that will lead to our entropy according to the Shannon entropy definition, where Shannon entropy is S is equal to Kb ln omega, or like Boltzmann entropy similarly, because there are different kind of definition of entropy, Shannon entropy, Boltzmann entropy, but the main anthem is same for all. So that will be S Kb ln omega or minus Kb pi ln pi, summation over that. So that is the thing. So we need to calculate the total microstates. I will give you one hint so that you can do that. The hint is here, the spin 1, that is you guys know, do not know. So if you have spin 1 equal to S, then the degeneracy is equal to 2S plus n, that is G. Okay, so for S equal to 1, G will be 3. So now these are, since these are distinguishable particle, so total number of microstate will be like Boltzmann constant, which is like G to the power n. So here G equal to 3, so that will be 3 to the power n. Okay, and so entropy is S is equal to Kb ln Wmb. So why Mb? Because this is distinguishable. Okay, and if you put this here, 3 to the power n, that becomes n Kb. Pretty simple, right? This is the right answer. Okay, got the point? Now I can ask you one extension problem. So using same thing, what will be for S equal to 3, then we just need to calculate G, which is 2s plus 1, that is 6 plus 1, that is 7. So using the same method, and that need to be distinguishable, right? Then we can write G times n, 7 times n, and the S will be, for S equal to 3 will be n Kb ln 7. Okay, quite simple, right? Got my point? So it's pretty simple. So I will try to keep it more generic, and so that you can take clues or you can take cues from these kind of discussions, and you can solve those problems in the exam. Okay, so rather than being specific, I will be more generic, and then I will come to the main problem, which will be a corollary or some kind of a special case of those generic problems. Okay, any questions so far? Okay, if not, let's move on to the next problem. Next problem says, which of the following statements is incorrect? So here can be two or more than one can be incorrect. Okay, so first thing says, indistinguishable particles obey Maxwell-Boltzmann statistics. This is wrong, right? So our says, first thing, Maxwell statistics valid for distinguishable particles. Okay, so this is indistinguishable, so this is incorrect. Second option says the integral spin particles obey Bose-Einstein statistics. That is also true. So Bose-Einstein particles or statistics valid for spin is equal to 0, 1, 2, so on. Means it's an integer. And we can also say those particles which have integral spins, they are Bose-Einstein particles or bosons. So I will write here, they are called bosons. Okay. So that is not incorrect, that is correct. Third option, protons obey Fermi-Dirac statistics. Now Fermi-Dirac statistics valid for spin is equals to half, 3 by 2, 5 by 2, so on. So these are half integer, these are called half integer particles. And protons which has spin half, so this is Fermi-Dirac statistics, FD statistics. There are also different FD statistics, protons, electrons, neutrons. Okay, these are called fermions. Okay, so this is also true, this is also true, this is also true. So this option is incorrect. Okay, clear my point? My point is clear. It is pretty easy, yeah? Right? Okay, so we will go to the next problem. Next problem says, which statistics do the particles that have antisymmetric wave function with respect to exchange of particles obey? So the particles with antisymmetric wave function, what kind of statistics they follow? So this is quite theory for you guys, but I will give you some tips or I will give you some informations which are more advanced, but there is no harm in knowing some advanced informations. Okay, so antisymmetric wave function means antisymmetric wave function means no two particles can have same wave function. No two particles can have same wave functions. That means they obey Pauli's exclusion principle or exclusive principle, whatever you can call. So, who follows Pauli's exclusion principle? Fermions follow Pauli's exclusion principle. Okay. So who are fermions? They follow Fermi Dirac statistics. Okay. This man, Dirac, is a wonderful scientist. He actually discovered hell lot of things. And he is one of the brightest minds in 21st. And you can say like he was in 20th century. And this Dirac was so, introvert. He actually thought of not receiving Nobel Prize. But his friends told him that if you do not receive Nobel Prize, then that will be a big news rather than receiving a Nobel Prize. So that's why he went there and accept the award, so that no fuss can be created around that. So that is the man Dirac. He was a fantastic scientist. Fantastic. How many extraordinary discoveries he actually did. Fantastic. He was one for the ages. He was a big man. Like starting from the quantum mechanics and the basic principles of he did research on the fundamental aspects of physics, and he built one of the fundamental pillars of physics, that is quantum mechanics or quantum physics. That's the man he is. Okay. So we'll quickly jump on to the next problem that says, consider a lattice with n sides and n green particles. Consider another lattice adjacent to the first with m sides and m red particles. Assume that the green and red particles cannot switch lattices. So what are given for red particles is there, what are given for green particles, that is also given. So that says the problem is, this is state A, the described state. What is the total number of configurations WA of the system in state A? So we have to calculate the total number of microstates or configurations. It is pretty easy. Just take few minutes, 4 to 5 minutes. Are you able to do it? Okay, I'll solve it. Okay, so so this is one lattice. There is kind of this thing, and there is a particle. It's these are let's this is M and M sides, and same. This is N and N. Now this is quite easy, right? So this guy and this guy do not talk to each other. So we will calculate this total microstate for this site and total microstate for, let's say this is red, and this is for green, and WA, the total microstate WA will be WG times WR. Since they are independent, okay. Now since they cannot switch lattices, so WG green will be choosing n sites from n, that is n c n or n factorial divided by n factorial divided by n minus n factorial, right? And WR is the same, that will be MCM, that is m factorial divided by small m factorial m minus m factorial. And so now if we WA will be then MWG times WR, that will be this option, right? So this is the correct option. Why? Because these are independent or cannot switch lattices. Cannot switch lattices. Okay. So that's the thing. Okay, understood? So we have to just calculate for green sites, we have to just calculate for the red sites or red particles, then we will product them together and we will get the microstates for the whole system. So when two subsystems are independent, then we will calculate independently the microstates for two subsystems and we will product them and we will take the product out and we will calculate the total microstates. Okay. Okay. Okay, so we will move to the next problem. Okay, so next problem kind of a continuation to the previous problem. Next problem says, continuation to the previous question, now assume there are n plus m sites are available to all the green and red particles. The particles remain distinguishable by their color. The particle remain distinguishable by their color. This is state B. And now what is the total number of configuration WB of the system? So now the thing is, obviously n plus m needs to be greater than m plus n. Means one condition is always there, okay? N plus m greater than m plus n. That is always there. Okay, this is state B. And there are, this is m, sorry. This is m, this is n. Now how can I do this? think about 2 minutes, because this is interesting. Okay, so okay, so one thing is sure, right, that n plus m factorial is total ways. Okay, now out of which n factorial ways green particles green particles is there, and m factorial would be red particles. So actually that would be n plus m, choosing n plus m, see how many how many lattice holes will be there. So lattice holes means there will be no particles occupied. Which is n plus m, capital N plus capital M minus capital minus n. So choosing this kind of lattice holes, so that will be n plus m minus m minus n. But that will give you n plus m factorial divided by m plus n factorial by n plus m minus n factorial. This would be the answer if those particles were indistinguishable, means they were not distinguishable by their colors. This should be the distributions. But here the thing is, they are distinguishable by their color. So this thing we will add more, there will be added more microstates due to the indistinguishability. So I will add one page and I will comment on that. Let me just quickly add one slide and go back to the problems. So if the particles were indistinguishable then the distribution would be, let me just write it by Wi, which is choosing m plus n particles or m plus n sites or small n plus small n sites out of n capital N plus capital M sites, that will give me n plus m factorial divided by m plus n factorial by n plus m minus n factorial. But these particles are distinguishable, right? But particles are distinguishable. So for that, more distributions will be added. Means out of those m plus n indistinguishable particle, how can we differentiate m green particles or n red particles? So the problem then comes, WD, which is distinguishable, is how can we distribute m green particles or n green particles from m plus n particles. So since these are red and green particles only, so choosing n green particles from m plus n particles will make you choose m rate particles from m plus n particles. That is actually m plus n Cm, means m plus n factorial divided by m factorial n factorial. So the total microstate Wb will be, what will be the microstate for indistinguishable, and then the distinguishability factor, which makes it n plus m, or n capital N plus capital M factorial divided by small m by small n factorial divided by n plus m minus n factorial times m plus n factorial divided by m factorial n factorial, right? So this will balance them each other. So capital M divided by m factorial n plus. This is an interesting problem. So this is the answer. Okay. So if I go back, so this is the answer, right? So just think about the thing, and I will take 5 to 6 minutes break. So during that, try to make sense out of this thing, and if you have any question, I will answer that. So the main anthem is, when there are total capital N plus capital M sites and small m plus small n particles, then we are left to choose small n plus small m number of particles out of those n plus m sites. Here we have considered that all the particles are indistinguishable. So that thing is done. We have did that thing. Now in our problem, that small m plus small n particles are distinguishable, and there are special type of distinguishability is there. They are either red or green. So now the problem then breaks down to, how can we choose n green particles or small m red particles out of those m plus n particles? That will be small m plus small n combined C m, and we will now product those microstates or distributions. This addition distribution which arises due to the distinguishability to the indistinguishable counting, and that we have done by taking the product of Wi times Wd, and if you do that, you will get the solution. Okay, so probably I hope I have clarified that. So just because this is quite conceptual problem, just think about it or just get through it. I will answer if you have any questions. I will take 5 to 10 minutes break. Now I hope it is clear to you. Okay, so let's move on to the next problem. Okay, so this is quite similar that problem that we have done in the just previous assignment session. The problem says, which of the two distributions shown in the figure below has the greater entropy? Now, if the four outcomes have similar distribution of probability, then they should have equal probabilities, equal entropy. So here 3/1/6 probability and 1/2 probability. So we can just checking those two, we can say that these two have same probability. So we will just calculate it for the thing. So we can just by saying, you can say that both have equal value of entropy. For outcome 1, that is S1, will be Kb, I will take common, will be half ln half minus 3 1/6 ln 1/6, and it will be for S2 also, like, because this is also 1/2 and 3 1/1/6 problem, 3/1/6 and 1/2. So this is the same thing, so this will be same probability, and the formula of S is Kb minus I Pi ln Pi. Okay, so both have equal probability. This is similar. Okay, problem 9 says, you have a fair six-sided die, means all the faces have same probability, or probability of getting 1, probability of getting 2, probability of getting 3, probability of getting 4, probability of getting 5, probability of getting 6 will be 1/6. Equal probable means fair. You want to roll it enough times to ensure that a 2 occurs at least once. What number of rolls K is required to ensure the probability is at least 2/3 that at least 1 will appear? Now, if that happens, so we will, let's say we have to roll for K times. So probability of having no 2 is 5/6 times K, probability of having no 2, and probability of having at least 1 2 is 1 minus 5/6 times K. Now this 1 minus 5/6 to the power K is 2/3, and we will solve it. 5/6 K is 1/3, and K ln 5/6 is ln 1/3, and if you solve it, ln of 1 divided by 3 times ln of 5 divided by 6, so it gives me 6.02, so it near about 6. Okay, simple problem. So we have to roll at least 6 times to get at least 1 2, and the probability of that is 2 by 3. Okay, so that is easy, right? It is very simple, right? So we will go to the next problem then. Next problem is the partition function for a two-level system, or the lower state at energy 0 of being non-degenerate, and the upper state is which is has energy epsilon being doubly degenerate, is given by. The partition function has this formula: z is e to the power minus beta epsilon. It is sum over epsilon, or energy. Sorry, this is energy and this is sum over energies. And beta is 1 by kBt. So we have energy E equal to 0 and epsilon, and there will be Gi, the degeneracy. So Z for equal to 0, there is no non-degenerate. So first will be 1 to the power minus 0 plus 2 times e to the power minus beta epsilon. That becomes 1 plus 2 to the power minus beta epsilon equals to 1 plus 2 exponential minus kBt. So the right option is option D. Okay, easy problem. Okay, now this is theory. Which of the following distributions correspond to the Bose-Einstein statistics? Why AI is the average number of particles occupying energy level epsilon I, and Wi is the degeneracy level of the ith level. This is called occupancy level. So for MB statistics, occupancy level AI is Wi exponential of minus alpha minus beta epsilon I. For FD statistics, AI is equal to Wi divided by exponential of minus alpha minus beta epsilon. Sorry, all will be plus. All will be plus. For BE statistics or boson statistics, Boson-Einstein statistics, this will be AI equal to Wi divided by minus 1. The generic formula is A equal to Wi divided by exponential of alpha plus beta epsilon I plus minus 1 for FD or BE, and Wi by exponential of alpha plus beta epsilon I for A. Okay, so this is the right option, right? Okay, so the similar problems but with different, different thing. So this way we can remember the things pretty well. Okay, now to the next problem. Next problem says which of the following expression is correct expression? So this is Boltzmann entropy, this is Shannon entropy, this is the entropy from thermodynamics. So all of the above. So all of the above will be T. So the Boltzmann entropy definition is B is KBLN. W is microstates. Shannon entropy, which actually make the connection between probability with entropy, is this. And thermodynamic entropy. So in the beginning I told you that there are different definitions of entropy, which is dq. Okay, so all of the above is right option. So entropy can be written in terms of different definitions. Okay, so here the says, which of the following distributions has the highest entropy? Okay, so let's just calculate it, but at the end of the calculations I will establish that what will be the highest entropic or what will be the most random distribution for this. We will establish that the system with highest entropy will have equal probable distributions. Okay, I will that I have probably established in the previous assignment session also, but today I will do it for this problem. Okay, so for the first thing, this is A, this is B, this is C, this is D. For A is equal to, let's KB take out, minus 2 times 1 by 8 ln 1 by 8 minus 4 by 8 ln 4 by 8 minus 2 by 8 ln 2 by 8. And if you do the calculations, so that becomes 25 ln 1 divided by 8 minus 0.5 ln 0.5 minus 0.25 ln. This gives you 1.213. 1.213 kb. Now for option B it is easy. S equal to kb minus 4 times 2 by 8 ln 2 by 8. There is 4 this kind of distributions. So that will give you 4, so 1.3863, 1.3863 C is KB minus 2 3 by 8 ln 3 by 8 minus 2 1 by 8 ln 1 by 8. And if you do this, this will comes to 1.22255, 1.255. D is kV minus 4 by 8 ln 4 by 8 minus 3 by 8 ln 3 by 8 minus 1 by 8 ln 1 by 8, and that gives you 0.5. So this is the least actually, 0.9743. So this is the maximum. So we can write that most equal probable distribution is the highest entropy. Okay, always remember that. So this is the correct option. Okay. So just think, so equal probable distribution is the highest probable distribution. So just think about it and try to grasp the thing, and if you have any questions I can answer it. Okay, let's move to the next problem. Problem says, what is the probability of drawing either a king or a spade in normal deck of 52 cards? So this is like I have did the theory in the beginning. So either or means this is the always write the. So is there any intersection between king and spade? Of course, there can be a king of spade, means the card will be spade, but it will be king of spade. So one card can be like this. So the probability of king is how many times? 4 by 52. That is 1 by 13. Probability of spade is how many? 13 cards out of 52. So 1 by 4. And then probability of king of spade means card is spade but which is king. This is 1 by 52. So the union, king union S is 1 by 13 plus 1 by 14 minus 1 by 52, and if you do this will be 17 by 52 minus 1, which comes 16 by 52. So this is the right option. So it's pretty simple problems. Okay. Okay, the last problem. It says, for a 3-level system in the following table, find the average energy. Okay. So average energy, how can we write it? What is the probability of that? P of E is Zi, if there are degeneracy, e to the power minus beta E divided by Z. So EPE will be E Gi e to the power minus beta E by Z. So average E is sum over all EPE pairs. So let's first get the partition function Z. So energy 0, so this is 2 e to the power minus 0 plus 2 e to the power minus 2 kBT by beta means 2 plus e to the power minus 4 kBT by beta means 4. This is Z. So E average will be 0 times 2 plus 2 kBT times 2 e to the power minus 2 plus 4 kBT times e to the power minus 4 divided by 2 plus 2 e to the power minus 2 plus e to the power minus 4. Please do this calculation for me. Please do the calculation. Okay, so I have done the calculations. It comes to 0.268 kBT. Okay, so this is the right answer approximately. Okay, so the further problems is this problem. This is long problems, so we'll take few times. Okay, yeah. So what the problem says? Problem says the energy difference between the lowest electronic state 1 is 0, where energy is taken to be 0, and the first excited state 3s1 of the helium atom is 159843 centimeter inverse. Here it is written in terms of wave number unit. Okay, I'll give you the unit converter. Okay, evaluate the fraction of excited atoms in He gas at 6000 Kelvin. Here says that these symbols indicate the states of atoms. Superscript says the spin multiplicity, as you have all know that spin multiplicity gives you the degeneracy, that is 2s plus 1, and 1 and 3 correspond to the degeneracy of the two-state systems. Now tell me one thing, which has higher energy, helium gas or helium liquid? Obviously helium gas, right? So higher energy state will be that. So we'll try to do that. Now probability of that, we know that probability of that energy E is Gi e to the power minus beta E divided by Z. So we'll first write the Z. What is the Z? Z first degeneracy is 1 e to the power minus 0 plus there is energy and degeneracy is 3 e to the power minus beta E. Now this E is now 1 centimeter inverse is equal to 1.986 into 10 to the power minus 23 joule. Now we will convert this, means beta P will be E by kBT. We will do the calculation for you guys. So there will be 1.59843 into 1.986 into 10 to the power minus 23 times there is 5, so 10 to the power 5 divided by 1.38, right? That is the Boltzmann constant, 10 to the power minus 23 into 6 into 10 to the power 3 Kelvin. Okay, so this cancels out, and if you do the calculations, then it boils down to this, and this beta E gives you actually so now what we will do to find the fraction PE, we will do this 3 times e to the power minus beta E by 1 plus 3 to the power minus beta E, and it is beta E is 1.59843 times 1.986 into 100 divided by 1.38 into 6, so 38.339. So if you do this 3 times minus answer divided by 1 plus 3 times, so it gives me to the power that gives you 6.7086 10 to the power minus. So this is the correct answer. So it's quite easy. Just you have to just do the numerics handful. Now problem 2. Problem 2 says a certain molecule can exist in either a non-degenerate single state where energy is taken to be 0 or a triplet state with degeneracy 3. The energy of the triplet exceeds that of the singlet by epsilon. Assuming that the molecules are distinguishable and independent, calculate the partition function. This is also like the same thing, just easy. Just do this thing for me. Just do this thing for me. So it is pretty simple, right? So as we have just said, Z will be Gi beta E. So three. So for it will be 1 to the power minus 0 plus 3 to the power minus epsilon by kb times temperature epsilon by k, means kb minus 1. So 1 plus 3 exponential minus 1. So if you do that, 1 plus 3, 2.1036. So it will be 2.1036. That is close to this. Quite easy, okay? Okay, so we'll go to the next problem. Next problem says, consider a system with energy levels epsilon j is equal to j epsilon and in molecules. If the average number energy is a epsilon, then the temperature is given by this. We have to find the temperature, okay? So the partition function, there is no degeneracy given. So the partition function z is z equal to 0 to infinity e to the power minus beta j epsilon, right? Okay, now this is an infinite series because e to the power minus beta j e or e to the power minus beta e always less than 1. Okay, so we can write as 1 by 1 plus, 1 minus e to the power minus beta e, because if you break it, it becomes first term 1, second term minus beta e to the power minus 2 beta e, so infinite gp. This is the partition function, right? Now average energy E is written as EPE, which can be written as summation over E to the power minus beta E by Z. So for this case, this is the case. Now, if you write the whole thing as, let's say, so we can write this as del beta to the power minus beta epsilon. So there will be one minus, so minus by Z. This is average. And this is also Z, right? So what it becomes is minus del beta del Z by 1 by Z. Or we can write minus del beta ln Z is equal to average energy. So this is one formula. Average energy can be written in terms of this. Okay, so I will add one page. Okay, so in our problem, Z is 1 by 1 minus e to the power minus beta e. So del Z beta is minus 1 square epsilon e to the power minus beta epsilon. Right? This will be the expression, and we know that average energy E is minus 1 by Z del Z by del beta, which is this expression. So then E becomes 1 by Z means minus 1 minus e to the power minus beta epsilon times 1 minus again epsilon e to the power minus beta e by 1 minus beta whole square. It will become epsilon e to the power minus beta epsilon divided by 1 minus e to the power minus beta epsilon. Now this is average energy A epsilon. So this epsilon epsilon cancel out. Now we get A equals to 1 by e to the power beta epsilon minus 1. Okay. Now just inverting it, to the power beta epsilon minus 1 is 1 by A. That makes e to the power beta epsilon equal to 1 plus 1 by A, and beta epsilon ln of 1 plus 1 by A, and beta equals to 1 by epsilon ln 1 plus 1 by A. Okay, so the right option will be option number D. Okay, so we will do the next problem quickly. Consider a system A consists of subsystem A1 and subsystem A2, and so consider a system A which has two subsystem A1 A2, for which this is W1 W2. Compute the entropy for the combined system. We said that for if we know the distribution for the subsystems, for the whole system it will be product. So WA will be W1 times W2. That will become 2 times 10 to the power 40. So entropy A will be KB ln WA, KB 40 ln 10 plus ln 2. That makes, in my calculation, it becomes 92.79 kb. 92.79 kb. So this is the correct option. Okay. Last problem says, this is the last problem for today, that a biological membrane contains n ion channel proteins. The fraction of the time that any protein is open to allow is to flow through is Q. Express the probability that m of the channels will be open at any given time. Very simple problem. This is kind of a binomial expression. So first to choosing m channels from n, that makes the W n C m. Now probability of this is the total number of microstates, and probability of that each event, probability of each such event is m times channel opening, that means Q times m, and not opening 1 minus Q times n minus m. So total probability that will become P m n will be Q to the power m 1 minus q n minus m ncm means n factorial m factorial n minus m factorial. Okay, so this is the right option, right? Okay, okay, so that's it. Okay, if you don't have any questions, then we can end the session here. So take care, good night, and please prepare for the exams and do join us for the next session. Okay, thank you.